There was one more thing that I wanted to mention that we didn't talk about in the last video regarding inverse functions in calculus. This is a theorem from the Larson calculus text, 10th edition. And I think it is obvious when you understand this formula, but I just wanted to reinforce these ideas. We said that f has an inverse if it's strictly monotonic, that is, it's increasing over its entire domain or decreasing it over its entire domain. So the question is, well, how does that relate to the graph of f inverse? Well, here are some facts. If the original function f has an inverse and it's continuous on its domain, then f inverse is continuous on its domain. If f is increasing on its domain, then f inverse is increasing on its domain. If f is decreasing on its domain, f inverse is decreasing on its domain. And we came up with this differentiation formula just using the chain rule in the last video. We said that if f is differentiable, f inverse is differentiable, and the derivative of f inverse at f of x is equal to 1 over f prime of x. So the slope of the inverse function, if this is my inverse, is 1 over the slope of the original function. But you have to be careful. You switch the roles of x and y. So the derivative of f inverse at its x value, which is the y value for the original function, is 1 over the slope of the original function at the corresponding x value. And that's what this says. It says if f is differentiable in the neighborhood of c and f prime of c is not 0, then f inverse is differentiable at f of c. So they're just plugging in c for x here. They're just saying as long as this isn't 0 and this derivative exists in some neighborhood around that x value, then you're good to go. Then this derivative is equal to this. This formula also implies the point number 2 and point number 3. If f is increasing, that means f prime is positive. So if f prime is positive, then 1 divided by f prime is also positive, so this function is increasing. If f is decreasing, that means f prime is negative. So then I have 1 divided by a negative number is a negative number. So if f is decreasing, f inverse is decreasing. And then differentiability implies continuity. So if f is continuous, and then we switch the roles of x and y, then f inverse is also going to be continuous. Actually, that's not related to differentiability, but I mean, I hope that makes sense to you, at least intuitively. We haven't proved that first statement, but the last 3 statements are suggested by this formula that we computed here. And again, I think this picture really helps a lot with that. Now, there was one other thing that I wanted to talk about. In the last video, I think we had f of x equals 1/4 x cubed plus x minus 1. And we said we can't actually state f inverse, but we know that f inverse of x equals y satisfies the following equation. You replace f of x with x, and you replace x with y. So this is a relation. It turns out to be a function, actually. And we graphed that function on Desmos.com. And the derivative of that function can be found using implicit differentiation. It's actually an excellent candidate for implicit differentiation. So we could differentiate both sides, assuming that y is a function of x. Get a 1 on the left-hand side equals, well, the derivative of this piece with respect to x, remembering that y is a function of x, is 1/4 times 3 times y to the 2nd power times the derivative of the inside, which is dy dx, plus the derivative of y with respect to x, which is just dy dx, plus the derivative of -1, which is 0. We can factor out that dy dx from both of those terms on the left-hand side. And then we've got 3/4 y cubed, or excuse me, y squared, plus 1 times dy dx equals 1. because dy dx times this is our first term, and dy dx times 1 is that second one. So we get dy dx is equal to 1 divided by 3/4 y squared plus 1. Now, if you're saying, that doesn't look right, that looks very familiar, but it doesn't look right. Remember what we said before, the derivative of f inverse actually, we said f inverse prime at f of x is equal to 1 over f prime of x. And then for that example, we said that f prime of x was 3/4 x squared plus 1. And that this was y. So we have f inverse of the original y value is equal to 1 divided by this the slope at the corresponding x value. Well, remember what happened. We said that if this is our original xy pair, x f of x, the new xy pair is f of x and x. So we switched the x and y. It's because we switched the x and y that this formula isn't exactly what we expected it to be. This is saying the derivative of f with respect to essentially y is equal to 1 over this function. But if we think of this as the x value, and it is the x value on our inverse graph, this could be x and then this would be y, and then we get this formula right here. So even though these look a little different, they're telling the same story. This is saying that the derivative of f inverse, where f inverse satisfies this equation, is equal to this. This is saying the derivative of f inverse at a y value for the corresponding inverse function is equal to 1 over that derivative at the corresponding x value. If we wanted to, we could switch that notation, switching the roles of x and y, and we'd get something that's more consistent with what we got using implicit differentiation. Now calling this the x value and that the y value, we get this formula, which is of course just the inverse function, or the inverse function of this guy, its derivative evaluated at the new y value. The new y value for us is x, because what was the x before is now the y, and what was the y before is now the x. So we get that. I hope that makes sense. If it doesn't make sense, just ignore it.